helical, yeah, helical. And why do we have them on helical? Why do we use a helical? Because I can have any orientation between the aerials, and because it's rotating, then it will pick up. So, yes, that's, we do actually see it. So Navstar, GLONASS, which is the Russian system, and there were great hopes that when the Cold War came to an end, that we'd be able to put these two together and end up with a really good system. But they are so different, and that doesn't seem to have happened. There's Galileo, which is the European attempt, which has not really got very far. So Navstar, services that we get from it. We have the precise positioning system or positioning service that is available to the US military. Don't forget the US military own this. And the US military and their friends. So you guys, as civilian users, will not have access to the precise positioning service. That is their authorised users only. What you will get is the standard positioning service, which is not as accurate. Comes in different segments. We break it down. There is the space segment. You all know about the space segment because we talk about satellite navigation, so that says you know about that. The numbers that are going to come up are based on geometric need. There are actually more satellites than this, but this is what you need to make the system work. So 24 satellites is what's needed. And they are in 6 orbital planes around the Earth. And those orbital planes, that's the equator, they're going across like that, so that angle there is 55 degrees. So inclined at 55 degrees as they go around. You can see why the question marks is like this. It's just full of junky numbers. 20,200 kilometres high. The GLONASS one is a little bit lower. It goes around every 12 hours. That's half a day, obviously. The GLONASS one, because it's a little bit lower, they've got to go around a little bit quicker in order to keep the centripetal force to keep it out. It's sad, but you do need these numbers. There is a masking angle. So if you think about flat Earth, almost, there's a masking angle 5 degrees each side. If the satellite is below that angle, then your equipment will disregard it. The reason for that is going back to this sort of Earth, is I've got my ionosphere and atmosphere above there, and if you're there and the satellite is over here, there will be a lot of distortion in the time getting there. And this system all works on distance, speed, and time. And it's looking at the time that the message left the satellite and the time it gets to you. That gives you a range from the satellite. And then you know where the satellites are, and you go, okay, I'm somewhere on that ring. So any difference in distortion there means it's travelled further, which means it's travelled longer, will shove you to a different place. So the accuracy, once you come to 5 degrees, they say is the distortion is too much. And yeah, there's a lot more satellites than is required. There's you. Authorised users, not you. Authorised users, unauthorised users, this is you. This control segment. So there's a master control station, then in Colorado, and then there are monitor reference stations, 6 monitor reference stations situated around the equator, as well as the Americans can find countries that will allow them to have their antennae there. So pretty much around the equator, a little bit above level, but they do quite well. Obviously, I need to communicate from the ground back up to the satellites that control this, so we've got antennae for that. And the control segment is forever monitoring, updating, doing maintenance work, corrections, all that sort of stuff. Ephemeris is the orbit. So ephemeris means orbit. Updates the clock errors. So the satellites have some really accurate clocks in them, but even accurate clocks have errors. And I mean, these are really accurate. There's something like 1 second in 1,000 years. But because we're talking about distance, speed and time, it's critical. We monitor the satellites for their operational status, which is called health. But, and some satellites can be taken out of operation because they're not transmitting correctly. So, basically, there are 2 frequencies that are transmitted. One is called the L1. The L1 is the one that you can receive, and it's transmitted on 1575. Now, they're not that often. They do ask you which frequencies, but fortunately, to date, they haven't gone pernickety with these little numbers here. So as long as you remember it's the 15, L1 and 15 and it's megahertz, you can find the right answer. They've not made it a big piggish about it. So you can receive that one. The precise position people will also have some coding on there, but you don't have access to that coding. Then there's the L2 frequency, which is on 12 something. Now if you remember, you've got to remember the 15 and 12. L looks like a 1, so the L2 you can stick to the 12, the other one then must be the 15. That's available to the military only. So they have access to 2 codes. And by having that, they then can make corrections to the ionosphere and the atmosphere that we can't make. So it makes them more accurate. They also have corrections made for if the US decided to destabilise the system to stop enemy dropping bombs on them, then they would have a means to correct that. So the Standard Positioning Service, that's what SPS is standing for, Standard Positioning Service. Position and timing, as I say, it's all coming from the L1. The Precise Positioning Service uses both. Accuracy, so if you're a precise position user, then its published accuracy is 1 to 3 meters. For us, we're talking about, sorry, jumped ahead, we're talking about minus 13 meters. So there's quite a discrepancy. 13 meters is not really enough to you be satisfied you're going to get to the centre line of a runway, is it? It's not really good enough. No. A couple of other codes don't seem to get mentioned, but we've got the M code and the L2C code, which is a second frequency available to civilians, which would mean you could make corrections to the atmosphere and ionosphere. So, what do we get? We get these satellites transmit what seems to be noise. It's almost indistinguishable from the noise that is in space. So it's called pseudo-random noise. That's what they transmit. And in that is actually a digital code. So it's a continuous transmission, but it's digital, and it works something like this. So while it's just going like that, that is like it's a 1 or a 0, whichever. When it needs to shift to go to the, say that was the 1, then it needs to shift to go to the 0, it reverses. So it will suddenly go. If it needs to then, that's the end of the 0 in terms of time, and then it will do that again, and so on. So it's a continuous transmission, but it has always been transmitted, but the phase is suddenly moved by 180 degrees. So that's called binary phased shift key, BPSK, which you might have seen. Binary phase shift keying. So we're making almost a key transmission, but it's continuous. We're getting binary information by shifting the phase. And we have an nav message. So how does it work? So this system of trilateration, we're going to use a few systems. Let's go there, and from that we are going to get latitude, longitude, altitude. That will be a 3D fix, and we also get time, so that's set to be a 4D fix. In terms of clocks, the space segment, each satellite has got 4 atomic clocks, so between them they maintain a really accurate time. And I remember seeing a programme, I think it was on BBC years ago, when this all first came out. You know that time happens at a different rate in space. That is accounted for in this system. So it's different. The master control has got atomic clocks. The fly in the ointment, so to speak, is you and your equipment, because you've got a cheapo quartz clock. So that's accurate, this is dreadfully inaccurate. And let's face it, it could have been you putting the time in, and you've come in with your watch from something that you took plus or minus a minute on a time fix. So its initial place is just way, way out. Excuse me. So what's in that transmission? It's got these elements to it. They've got this pseudo-random noise. It says, I am this satellite, this is me, and this is the time that I'm sending the message. So there's the time included in there, so that you can go, okay, it was transmitted then, I got it here, I'm that distance from the satellite. In the nav message, there is the almanac. An almanac is an Arabic word meaning a map of the stars, effectively. So it's a map of the whole system of where things should be at certain times. Ephemeris, then, we talk about the precise position of that particular satellite. It's where am I? A satellite clock correction. So the monitor station is always monitoring what's going on, excuse me, and can see that there is a tiny, tiny error in a satellite clock, but it will send a correction in the message so that you can take account of that error. Then, of course, you need to turn that to UTC, because you're not interested in space-time or satellite time, you're interested in UTC, so there's a correction for that. There is a direction, if you like, for the ionosphere. The ionosphere is fairly predictable, isn't it? Sun comes up, it becomes active, sun comes down, it loses activity, and some of it disappears. That distorts the wave, but because it's predictable, we can make an approximate model of it. So you get that. Unfortunately, the atmosphere, which is a lot thicker than the ionosphere, is so unpredictable that there isn't a model for it. So that is an error that we have. And a bit about the status of the satellites. Now, the bit really that's most important on this slide is that bit. It takes 12.5 minutes to run through this message. It's possible that you come in, you just missed that, so you're running through all of this using it, and you know, because it's a continuous thing. You missed that, and then you're coming through there. I need it.
That was weird. What happened? Where'd he go?
He got called.
Huh?
He's not needed.
Alright.
Or, maybe read radio waves.
Probably.
He picked up the difference between 90 and 150 hertz. Told him to move in that direction.
Right in the middle.
Yeah. Who knows?
How's it going? Yeah.
I got really ill last night.
Really?
Fever all night.
Really?
Yeah. Really shaking this morning.
How you know?
Good.
You want to have some...
Struggling. You got paracetamol?
I've got paracetamol caffeine.
I'll have it
You have it?
in a bit. I'll see how I get on.
I have the good one for a really strong one.
Okay. I'll wait for a bit and I'll see how I
Let
get
me
on.
know.
Thanks a lot. Yeah, that's good to know.
Always carry me just in case.
Yeah, it's a good idea. I was going to stop this morning and I just didn't have the energy to stop and go around the supermarket. I just didn't want to do that.
It's the worst thing is being sick doing these things.
Yeah. It'll be worse next week though, in the exam.
Oh God. I hope you're not going to feel sick then.